Okay, good morning. This is the last lecture, and by definition, the most important. So I'll try to separate more or less equally 3 subjects in 3 half an hours, and at the end, I'll try to maybe summarize, and not any kind of knowledge, again, that it's impossible to in 5 lectures give you a knowledge which normally is a 1 year, 2 semester course. But I'll try to, again, as researcher to researcher, tell you what I see as a picture where main action could be in next, I don't know, 10, 20 years. That's maybe the most interesting thing. And of course, with the usual caveat that we're usually wrong in predicting future. It's very difficult. Okay, so last time we realized that information is life, that it's actually life-sustaining substance is information. And now, today, of course, will be no less important subject that information is money. So I want to tell you some simple problem, and then maybe a few more ambitious tasks. Again, I'm so old, I remember this transition where people who know what is free energy can solve differential equation what somehow overnight appeared to be thought by Wall Street. I was at Princeton at the time, and I just remember it was 96, that there is a job fair at spring, and there were usually people coming from different places because most of the people don't go into, some graduate school or academia. Most people go and look for jobs. And there were a lot of people from Wall Street. Like last year, there were a lot of people, and they were looking for fresh graduates from physics and mathematics. And I remember that was really quite, and several of students of mine went and did very successful. Of course, this was already after Jim Simons, when they had shown him what is a great mathematician can do when he starts thinking about a right way of money. Now, when you look at, like 25 years later, you realize that they were mostly about technicalities, right? And we are good at technicalities. At some point, I remember I met a friend who went there, and he excitedly started to tell me that he solves the problem of so-called Japanese options. And this is a problem where you have a random process, it just wanders in space, but sometimes gets to the surface. And it can stay stuck to the surface, and then it can get over. Okay? For them, stuck to the surface means that the price of the option turns 0, just nobody needs it. But it not necessarily stays that forever, it has a finite probability to be unstuck and go. And he solved this problem, he found probability distribution, some Bessel function. You assume that it's a wide process, and so you write some kind of Fokker-Planck equation, you solve it. And I remember listening to him, and when he was talking, I say, that will be Bessel function. He say, how would you know it's Bessel function? I say, because I had a student who was considering compressible turbulence and incompressible flow, you have 2 fluid particles, which generally, but sometimes, because it's compressible, they can get together. But then again, with some finite probabilities, that can get unstuck. We are very good at solving such types of problems, and we are still sought after, and I sometimes go to stock exchange conferences and all this. But so I'll start from such problem, show you how it actually solved. But then maybe after that, I'll try to talk about more conceptual things, which nobody solved, and which if anybody could solve, that would probably will be physicists. So let's do gambling. Okay, so you have some money, and let's start from the simplest game, namely that it's just coin game. So you throw a coin. If one side, which you predicted, wins, you get doubled your bet. If you lose, you lose. Your bet just goes to the winner. Okay. So what you need to do, you need to decide on which side to bet, right? And how much money out of your money. Of course, if you are not idiot, you understand that you don't bet on equal probabilities, but you have an information that one side has a probability which is strictly larger than 1/2. Okay? Let's call it winning side. Okay? Oh, in this case, you are ready to enter the game. And you want this game to be repeatable. Namely, you want to play it over and over and over, multiply somehow on average your money if you win by twice. So you need to decide what fraction of your money to put into winning side. You want to maximize a return, right? Namely, amount of money that you will have after n games. What is its random variable? So you want to maximize the expectation value of it. Okay? So what would be the maximal and the mean value of return? Right? When you realize that if you're just betting all your money on the winning side, every time it comes with a probability p and multiplies by 2. So your average return would be 2p in the power n. Right? And this is also the maximal return. Because any other realization in which on the way out of n you lose immediately, that the game is over for you, right? Because you lost all your money. But if you bet all your money always on a winning side, that's your return. P larger than 1/2, right? It's exponentially growing sum of money, but it would be a wrong way to do it, right? Why? If there will be many people and all betting by this strategy, okay, then there is a probability of this winning. What is the probability of this chain of events, or as we would say, this realization of a random process to happen? What's the probability? Every time probability of winning is p. Every throw is independent. So it's p to the n, and it approaches 0 exponentially fast, right? So of course, and this is a very good illustration of what often is called intermittency, or it's a very non-Gaussian statistics, right? So all your mean comes from a single event. Any other event, any other realization includes at least one lost, and that's it. You had 0. So you realize that it's probably not a good strategy to put all your money on the winning side. That's why you ask about fraction. Okay? So you say, okay, let me put a fraction of my money on a winning side. What to do with 1 minus f of your money? Huh? You can keep it as an insurance in case you win, you lose this money. But on the other hand, if in this case, in this game, this time you lost your money, that means other side won. So it seems like a smart strategy to put 1 over f on the other side. Because if in some case you lose, then at least this would be doubled. Okay? So now you are saying that let me say that by what factor you could amplify your game. So you would say that I would twice f, and let's say it happened nth time, and it will be twice 1 over f, which would happen n minus n times. Now, for any realization, n is a fluctuating numbers, right? For different realization, numbers for which winning side wins, it's fluctuating. We know its mean average of it, it's p. But generally in a realization, let me write it as 2 in the power n times, how I call it, lambda capital. Yeah, let's call it lambda capital. And let's now concentrate on this lambda, not on the exponent of it. This is your growth rate of your money. As any rate, it will probably has to do something with an entropy. Entropy is always a rate. Rate is always some entropy. Again, it's a fluctuating quantity from process to process. And average of it would be called a geometric mean. This is arithmetic mean. Just, you get that money plus that money plus that money, divide by. But now you try to compute geometric mean. It's a function of f. So apparently it is 1 plus n over n log f plus 1 minus n over n log 1 minus f. Okay? So that's your thing. Now, if you're really interested in averaging, namely you take a limit of n going to infinity, and then you realize that now you know the limit of this quantity, right? What is the limit of this quantity? It's a fraction of wins of your site, which is p. So you now know that this is 1 plus p log f plus 1 minus p log 1 minus f.
Shouldn't there be brackets in the first term, 1 plus p?
This 1 minus p.
In the first one.
What do you mean brackets? This is p log f. P log f. Well, this is come from here.
Okay.
You take log of it, n would come here, you divide by n, and this 2 gives you this, this one. You take log 2. Okay, good. So now, I mean, what is left? Just trivial differentiation. You ask d lambda df must be equal to 0. Okay, then you just differentiate this, give you p over f, give you 1 minus p. So you need to solve the equation that p over f plus 1 minus p 1 minus f equal to 0. And of course, it's minus. And of course, the answer is f equal to p. And it's a very famous thing. It's called proportional gambling. But it's called proportional gambling when you're going to Department of Economics of Business School. If you go to biology, it's called phenotype switching. The same formula. What is phenotype switching is that you look at, for example, population of bacteria, right? And then you recognize that the almost not any population of bacteria, at least on 2 basic properties of metabolism, belongs to 2 types. One type is usually fast growing but vulnerable to things like antibiotics or other environmentally harmful factors. And another fraction of population of bacteria is usually slower growing but are more resistant. Okay? And then you can do experiments in the lab, or you can feed them antibiotic and see how this fraction changes. And you realize that this fraction, namely how much population is allocated to this phenotype or to that phenotype, depends on the statistics of the environment, which is the probability of winning or losing, right? And it's a really very impressive body of research. And of course, it's not only bacteria. For example, you go to the forest, and in many, many forests, it's not all seeds which come out from trees or bushes, they germinate. The fraction of it is kind of left for next year, sometimes few years. Forest fires play a very important role in germinating seeds. So it's a very fascinating. When long ago we organized a physics of climate program at Aspen, and there were different people, in particular there were people from forest fires. And we learned a lot, and they learned also from us a lot of statistical things. It's very, but it's essentially the same formula. What I gave you a simplest version of it, but you get the gist. It's proportional gambling, right? Now you can ask what is now your maximal growth rate, and you find out that it is plus p log p plus 1 minus p log 1 minus p. Well, you recognize this formula, right? What is this? It's entropy of this distribution with a sign minus. So let me write this formula in the following form. I write this as an entropy of a uniform distribution. If my probabilities were half-half, my entropy would be 1 bit. Everything is in bits here. So it's S of u minus S of p. This simple formula is kind of, I mean, all this textbook of financial mathematics, they essentially follow from here and up, plus random walks in a space of prices. So what it tells you, the rate with which your money grow, this is rate, it multiplied by a number of attempts, is an amount of information that you get, right? That's uniform minus what you've got, okay? So the more information you get, namely, the more non-uniform is this distribution, and you know it, this gives you the rate, okay? Good. Now let's play this game in a little bit more general setting. So now we can go and bet on different stocks. We can buy different stocks, not only one, two sides of one coin. Or you can think about horse races. So this is another nice metaphor for it. Okay? So now you have I runs from 1 to k, let's say, okay? And every stock has its own pi, but also they generally give different payoffs, or particularly when you think about horse racing, then different horses, they give different payoffs, right? So there are, let's call it GIs, okay? And now you would say that what you really need to maximize is the sum over I, pi log. Again, we are maximizing geometric growth rate, right? So your lambda p log f I g I. Right? So this much money you put, that's a fraction you put in the stocks, and it's multiplied by the payoff that you get, and it's a log because you compute a geometric mean, and it comes with this probability. So now when you will differentiate this with respect to f, you immediately recognize that payoff are irrelevant. Well, they are relevant when you count your money, but when you're making your choices, only probabilities matters. And of course, it's clear that, again, the same proportional gambling work over here. And so you lambda, now it depends on p's and g's, your growth rate is a sum over pi log pi gi. Okay, but now the point is that the operator is not an idiot, right? Or market makers or somebody who sets the prices of stocks, which would essentially determine the payoff, and operator of a racetrack who sets payoffs, right? So usually the operator also thinks about probabilities, and he thinks that if the probability of this horse winning is high, then the payoff on it will be low. And if the probability of it low, then payoff is high, because you would expect that not many people. We would say that would give GIs 1 over PI, but it's even worse. He needs to, to feed the horses, and there are expenses involved in keeping racetrack. So he usually, interesting that it's always Z in all this economic literature, which is a partition function, come to think about it. But I always put it Z, and Z is some factor which is larger than unity. When you plug it here, you recognize that your lambda is negative, kind of, no matter you do. Okay? But then, okay, you can say, I mean, look, it depends who gets what probabilities, because the probabilities aren't written, aren't given to anyone with a ticket to racetrack. There are some kind of previous histories and huge tables, and there is a lot of information about what actually happened in this race in this country, with this horse, or in this, etc. So in principle, you can say that maybe the operator actually using another distribution, QI. Okay? So that what actually would stand here, your lambda on P and Q would be now minus logarithm Z. I plug this formula plus sum of Pi log Pi over Qi, which we immediately recognize is, what is this? It's a relative entropy, absolutely. It's d of PQ. Again, what you learn is that you, in principle, can overcome the natural friction in the system, which are losses, right? If your probability is better and relative entropy measures how much. Again, think about it. If your distribution is closer to the real one, I mean, even yours could be wrong and his would be wrong. The question is which one is closer. And as you're closer to it, namely to a true entropy of the distribution, you can encode the same information, let's say the tables of all past wins or loses shorter, right? So, and this is amazing thing which economic students always kind of learn by heart, that the better you can encode your information, I mean, or the past events, the more is the rate of your winning money, okay? So that's a simple message out of here. Now, what may be a general remark, that as we discussed, arithmetic mean, if p is larger than half, is always larger than unity, right? A geometric mean, not necessarily. As we discussed, depending on what is your p and q, this could be negative, right? And it's a general statement that, if you take a logarithm of it, right? So logarithm of some a, and and this could be larger than unity, but if you take exponent if your a is exponent in lambda, and you take a logarithm of a which is lambda, and then you average, it could be negative, right? So this simple lesson is that by convexity of a logarithm, right? Convexity of this is a, right? So convexity of a logarithm means that it could be negative even when average of quantity itself, namely the logarithm of the average, is larger than unity. Don't play such games, evidently, right? Because even though average means are larger than unity, it happens with a vanishing probability. On the other hand, when you look at this formula for lambda, right, you recognize, you remember that this lambda was now it's p. When n goes to infinity, it is what is called self-averaging quantity. Lyapunov exponent is of this type. That's the reason why you average logarithm. Because this quantity happens with probability fast approaching unity, right? This quantity very fast approaches p as you go, because again it's a sum of random numbers. Every win or lose changes it additively, right? So this is really an important lesson here, and this is essentially, if you think about it, this when I'm thinking about this message, always average logarithm. This is why when you average logarithm, this is the result which comes in overwhelming amount of realization. And as you go to infinity in your sequence, etc., it comes with a probability fast approaching unity. And these guys comes with a probability fast approaching zero. Okay? So that's the difference between geometric and arithmetic mean. Now, maybe just a side remark, because we're already finishing the first half an hour. Of course, racetracks do not operate according to this. So how real racetrack operates, What statistics racetrack operators and a lot of people who really what is money makers at stock market, what statistics they are really interested in? Not in the statistics of horses winning. They are interested in the statistics of people betting. People don't bet according to, they don't go study all this. Some people do, and they also fool themselves, If you never ever invested, when I was young like you, and again, all this craze happened, and we thought, okay, theoretical physicists must be, and everyone look at Jim Simons. I used to know him. And so, okay, I'll go and I'll bet on the stock market, which I actually did when I was young and foolish. And then I've realized that I don't do it according to any probabilities. And there are many things that you learn about yourself when sometimes you win, sometimes you lose. But so people bet according to their whims, and operators study the statistics of betting, which is very easy because that's what they have in their books, right? And they put GIs according to these statistics. And if you look in the book at the respective chapter, which calls information is money, there is a nice problem there about if you are a racetrack operator, you have the statistics of horse winning, and then you have a statistics of people betting. How you would put payoffs according to which? And you realize that, of course, in the long runs of many, many races, the statistics of horses start playing. But the statistics of people betting plays in every race, because there are very many people betting each time. Okay? So this is immediately a self-averaged quantity. And of course, which tells you that horse racing and many other things is a pure sport. The profit of race operator does not depend on the result of the race, most of the time. Well, there are events and there are nice movies about it, but operators get their money no matter which force win or lose, because they put payoffs according to probabilities of people betting. Okay, that's also a very important life lesson here. Okay, maybe last thing about it is that at some point I really encourage you to think about money as a statistical physicist. I already mentioned in the first lecture that it's pretty easy for a physicist, and people actually already started to do it, to put the idea of purchasing power of money into free energy form, right? Like you say that this formula that E minus TS, if you say that your purchasing power, if your money minus some factor, let's say minus information, okay, or plus information, because entropy is minus information. So what it tells you, that if you have less information, a purchasing amount of the same money goes down. That's easy, relatively. Well, it's a lot of technical things to be done here, but nature of money itself is something which is totally mysterious. Again, in payments, it's like energy. In keeping records, it's like entropy. Also, the general amount of money increases monotonically until the crisis happens. But even more interesting, and I think that would be for your generation, is things like crypto. Because it's very interesting when there are different monies around, right? So you started to understand something if you really have access to different forms of it, right? You better understand energy when you understand that there is potential energy and kinetic energy and different forms. So, for example, credit card. Who guarantees credit card? Bank. Cash. Who guarantees cash? Government. In general, it's two different forms of money. Now, crypto. Who guarantees crypto? Crypto exchange. Okay. Now, how, and just look at these wild fluctuations of crypto, right? Because most of it is because the price of money, because after all, you ask how this money is exchanged with this money, right? And then you realize that it very much depends on how much people actually using this money. Because money is a social construct, right? It's like an agreement between people. Because generally, I mean, these coins or banknotes, they just means nothing, right? Like a gold. Gold also means nothing. Well, there is a very little kind of practical use of it. And this is very interesting. When I'm thinking about it, how I would try to put in any framework of statistical physics or information theory, which is the same thing, it's doable, but it needs somehow kind of a new conceptual framework to put this idea, like how you can quantify the degree of trust and then use it in this thing. And another thing about money, this is already people started to write, even though I have not seen yet anything really useful, is what is called arbitrage. Arbitrage is, for example, you have rupees, right? You go, you buy dollars, because in dollars you can invest this money, or you just expect that the exchange rate would change. And then after some time in the future, you buy rupees back from your dollars, okay? So what you did, you created a closed loop in a space which is currency's time. You get back to the same point, you got something. It's gauge field theory, right? So you have a gauge field, and then you can use all the machinery of gauge field theory trying to describe what economists call arbitrage. I think that's an interesting direction, but so far it's just kind of started, okay? Good. So now I finish at this point and we go quantum. Any questions about money? Except where to get them? No? Yes?
It's also trust in time, right? Like, for example,
Huh?
when you say money, so about trust, there's also a factor of time, right? Because sometimes you issue money with the idea that in the future.
Everything about time, absolutely right. The time is really important here. Everything happens in time, arbitrage happens in time, etc. So it's really, money, well, originally, right, there was just exchanging and there was barter. At some point, money was like a keeping track. Temporal and probabilistic aspect appear at the point of credit. The moment credit appeared, money acquired temporal element and probabilistic element. Okay, and from that it just goes. Okay, I think it's fascinating subject, and that's actually for your generation, you know, to do breakthroughs in this stuff. Questions? Yes.
So when you spoke of arbitrage and comparing that to a statistical physics framework, I mean, when you talk about a statistical physics framework, you typically expect that everything is almost correlated with everything, and things are almost efficient.
No, when I'm talking, yeah, efficient is the right word, but not everything. When I mean statistical framework, what we can do, what we actually very good, what is the best in the world in doing, in finding extremal functionals. That's essentially what we're doing. And then we teach like everyone, you know, self-driving cars does it, AI does it, kind of optimizing functional, looking for, the question is which functional in which space, that's it. It all boils down to this. Because then optimizing, I mean, engineers do this better than us, right? We just need to write the functional. That was our game, right? So when I'm saying put in this framework, because this M plus I, it's easy. I mean, all this phenotype switching, of course, biophysicists wrote this functional, which incidentally is a growth rate, is one part of it, plus mutual information between internal state of bacteria and external state. Bacteria needs to know, for example, how much enzyme to generate from genome, but it depends on how much factor is outside, how much you need this enzyme. But acquiring this information needs metabolism. So you always wait. But so far, as I said, all our functional are two terms. There may be more complicated functionals, but we can't do it yet. Okay, go quantum. So what I now want to, and this is the last part of this course, but this is a whole chapter in the book, is I want to show you that the fact that information is physical has profound consequences for information itself. There are two statements. One already I made is from Landauer, information is physical. And at the end of this lecture, I promise, if I forget, you remind me, is a statement from John Wheeler, is that physics is informational. He even coined a great sentence, which I put on the back of my book. And he says that he thinks that that all physical processes are essentially about information. Okay, it's a very, very non-trivial idea, and he encoded it in these three words: it from bit. Okay, now what we'll be talking now for the remaining time is that the fact that information is physical, it exists in a physical world, imposes limits. Because so far we were talking that information we measured by the amount of uncertainty which it removes, right? Mutual information measures how much uncertainty about B you remove by measuring A. In principle, it could be as little or as large as possible. Now what I want to tell you is that the fact that there exists fundamental constant. And as I say, there are three fundamental constants in this world. Let me write them here. They are h bar, speed of light, and gravitational constant. So far, I mean, as far as we go, they are independent. And they have numerical value. And that imposes restriction on the amount of uncertainty in the world. One restriction is evident, you all know it. I just now write it in the most general form so that you can see it. And this is quantum uncertainty. So the fact that there is h bar, fortunately it's a very small number, restricts uncertainty from below. No matter what, our uncertainty about any physical object, any, could not be less than some lower bound. What is really surprising, that these two other guys, when they join this, they impose a bound of uncertainty from above. Your uncertainty about a given physical system in a given size of space with a given energy could not be larger than. Which means you cannot squeeze more information into a given region of space. Okay? So that's the subject of what we'll now be talking about. So first of all, let me remind you that what is quantum mechanics? It's quite bizarre science. Mathematically it's trivial because it's just linear algebra. But physically it's bizarre. It tells you that every state of a physical system can be described by a vector, just some complex vector. The strange thing is that physical system can exist in a superposition of these vectors, even though they could be eigenvectors of some operator. And by operator, we mean now matrix. So there is matrix, and if we have operators, I don't know, some O, and we have vectors, some kind of psi, then this is a vector. This acting on this is again a vector. We can make an inner product, and this describes expectation value or average over many measurements of a given value. This could be Hamiltonian, and then it's energy. Now, measurement is totally bizarre thing because it's an interaction of quantum mechanics with a classical object. It immediately collapses superposition into a single way. Probably uncertainty of quantum mechanics conceptually related to the fact that it's not a closed science. For its definition, it needs measurement which is interaction with object which does not satisfy quantum mechanics. It's probably not unsurmountable. At some point, I think that will develop, and that would be probably more mathematical nature. We really show how properly take your measurement device as also quantum, start increasing degrees of freedom there, and then show that interaction of any quantum system with a finite number of states and this infinite limit would eventually collapse this. It's probably doable, but nobody did it before, even though when I was a student, this collapse of wave function was considered like totally bizarre. Now it's kind of less. People think that maybe we can do some progress. Anyway, so now let's consider what are the consequences of it. Well, first of all, there is this uncertainty relation, which is pretty trivial. It says that if you have an operator X and an operator Z, then each one acting on a state project it on a state with kind of measuring this quantity in this sense, right? But if you do it first Z and then X, that means that you first would measure Z and then you would measure X. But you can do it other way around. You can do it ZX. Now, if these values that you measure, X and Z, could simultaneously exist, namely have the definite value, then this difference is zero. This difference is commutator, as you know. But generally, matrices do not commute. And that means that you would have, you can impose conditions of it. For example, if you just take this, which is commutator, and do it psi-psi, that's pretty straightforward to show what Heisenberg did. I knew a guy who was at Princeton, at Göttingen at 26, and he says there was Heisenberg returned from vacation and shown to everyone these big tables, and there was, this stuff. And they said, what are these tables? And then he said, well, you do it like this times this. Say, yeah, but then Born told that it's called matrices. They did not know. Anyway, it's less or equal than 4 psi x squared times psi z squared. So now what you find out is those are variances, and so you think you see that if this is non-zero, then your variances are bound. Now this relation, of course, is something which is dependent by states. So for different states, you have different answers. So you may be interested, could we put an absolute limit of it, which means that there are some states for which this would be kind of minimal. And we know, for example, that if our x is p, which is eh ddx, and our another is x, then their commutator is h bar, and you can find, which is pretty straightforward, if you take these psi states which are Gaussian in coordinate, then they will be Gaussian in momentum, because this is just Fourier transform, and they realize the limit. And in this limit, you can formulate this statement as essentially Heisenberg formulated it as a variance of p times variance of q. And if you take a square root and it's larger than or equal than d, which is a number of dimensions, times h over bar. That's the way Heisenberg wrote it, and it took another 50 years when we generalized it. Because this, look, this is a statement which is about operators. It's not about states, right? But of course it was written for a Gaussian states, and it was done by Dech, I guess sometime at 60s or 70s. Then you can write it, just kind of rewrite all this as a logarithm of 2 sigma pi over h plus logarithm 2 sigma q over h, which is entropy of a Gaussian p distribution plus entropy of a Gaussian, well, q distribution, qx, and it's larger or equal than log d. Well, d is the dimensionality of your space. So this is kind of a modern way of rewriting this relation, but you can do it kind of a little bit more formally, because you say, what does it mean that these two operators don't commute? What I mean, the simple geometry behind this algebraic statement, right? The geometry is that if you take x and you find a basis in which you diagonalize x, then z would be non-diagonal in this basis. The non-commutation of two matrices means that they cannot be diagonalized in the same basis. So you understand that essentially what this means, it means some kind of a non-orthogonality. So you can rewrite this statement. And again, I'm not deriving things, because more or less I cannot teach you quantum mechanics in half an hour. I'm just assuming that you know quantum mechanics. I'm presenting it in a little bit different form so that it would nicely fit into information theory. So you may actually say that if you have two things, x and z, and let's now do it more generally. So S, entropy of x. What does it mean, entropy of x? I'm now writing classical Shannon entropy. Namely, I'm saying that I have x operator. It gives me measurements. This measurement has some statistics of its value. For any statistical distribution, I can compute its entropy. So it's a Shannon entropy of measurements. Okay? Any measurements give you classical results. It has probability plus S of z, and this is larger or equal than logarithm of maximum of x z squared. This, if you can diagonalize this, then you realize that you can make it like this, then all the vectors are orthonormal. But because in general you cannot, then what is here is the degree of non-orthogonality of two bases x and z. And it's called mutually unbiased if on average projection of any x eigenvector on any z eigenvector is 1 over d. That this is unbiased situation, is when all this is just 1 over d. Okay? Well, this is probably 1, yeah. Logarithm, this is minus 1. Okay? So this is, in general, this 1 over d for unbiased basis. So this is uncertainty relation in its most general form, as now quantum mechanics writes it. But there are two sources of uncertainty in quantum world, and this is the fundamental uncertainty of quantum mechanics. But there is also an uncertainty which comes out of quantum statistics. And quantum statistics is because we consider subsystem, and the subsystem could be entangled with the rest. But there is a principal difference between quantum statistics and classical statistics. In classical statistics, we can always say, you can learn more about this, you can learn more, you can learn more, and you can actually consider kind of more and more information. Entropy is not only about system, it's how much you know or control about your system. In quantum mechanics, in a sense, the need in statistics is fundamental, because this uncertainty means, in a very simple terms, you cannot localize your system in space, right? Because why P and Q are so important, right? Because our phase space is PQ, right? To know something about system is to give the coordinate in the phase space, but we cannot. It cannot be localized, neither in P direction nor in Q direction. So entanglement in this sense is fundamental. There's no quantum system which could be really localized, and in the third half hour we'll see how dramatically it plays in other settings. So what is now, I want to just write you a most general uncertainty relation for quantum system, and let me do it like this. So I just leave it like here, and so I assume that after all the Prabha lectures, you know what is von Neumann entropy, and unfortunately in the present books they never give, at least not even this Chen and or Preskel book, they never give original von Neumann argument. It's in my book, you can find it. It's really his very simple but non-trivial argument why you really can define such entropy. Landau actually did it first. 1927, almost the same year, they published and essentially von Neumann generalized. So what now I want to consider you how you write a very general relation, and you would be not surprised probably that it all follows from relative entropy, which is a very general thing. So let me define, again, I have the same x and z operators. They do not, let me erase it and just kind of, in a moment it will appear in a more general form. So I have a rho, which is a density metric. You know that I can define S of rho, which is a trace of rho log rho. Again, let me remind you what you know, and Prabha taught you that you can take this matrix and diagonalize it. And in this diagonal form, it has positive eigenvalues staying in the diagonal, and the sum of these eigenvalues is unity, and you can treat them as a classical probability distribution, and the Shannon entropy of this classical probability distribution, namely of eigenvalues of density matrix, is by definition your von Neumann entropy. You can write your matrix in any other representation, but if you want to know what is this quantum entanglement entropy, it is the classical Shannon entropy of its eigenvalues. Okay, good. Now, what you can do with this rho, you can take this x and z operator and do two projections, okay? Let's call the projection mx rho, and I call it rho x. Projection on the states in which my x operator is diagonal. It's an orthonormal basis. So there is some kind of orthonormal basis of these states, but there is also orthonormal basis of these states. They are non-orthogonal to each other, but each one is orthonormal, and your matrix is diagonal there. So now you can define for every such matrix, you can define S of rho x, which is, of course, just S of x, namely, which is the Shannon entropy of eigenvalues, because this is already in the basis in which it is not only diagonal, but eigenvalues give you probabilities of different values of s, of x. Then this is just, and the same you can do, of course, for z, s of z. Now what I want to do, which you probably won't be surprised, at this point, I defined a relative entropy, let's say between rho and rho x. And of course, I defined it as a usual way, just with a little bit of accuracy, because now I kind of all these matrices. So I write it like this. Okay, let me write it like this. Minus rho x. Okay, this is rho log rho over rho x. Technically, right? This is a minus here. But then again, by nature of trace rho log rho x, because it's a diagonal matrix, is the same as a trace log rho minus trace rho x log rho x. Okay? And then you recognize that this relative entropy, this is your minus s of rho, and that is minus s of x. So it's s of x minus s of rho, which is larger or equal than 0 by definition for every relative entropy. It essentially tells you that projection increases uncertainty. So in a sense that s of x is larger than, the same, of course, is true for s of z. Good. But now you use a little bit more non-trivial property of any entropy. And I did not have time to do it because it's really something which you need like 30, 40 minutes to really show. It's called monotonicity. And this property is fundamental, particularly in quantum information theory, but also in classical. Monotonicity means that if you observe less, I mentioned it on tutorial, I mentioned it. If you observe less variables, then generally your kind of mutual information is less, right? Or relative, because it's, well, to put it simply, if you have x, y, z, and you try to distinguish distribution, it's easier that if you look only on x and y, namely you trace out z or average over z. Because, you know, if you look at more directions, there are more differences in general you see. So this monotonicity is very intuitive property. Let me write what I mean specifically here. Specifically, I mean that if you look at this d rho x, this is larger or equal to d mz mx rho, namely, I just took, no, just mz rho x. So any projection, you know, it increases your uncertainty and it diminishes your relative entropy because you now have less to observe. A proof of it, like, I don't know, 5 pages in this textbook on quantum information. And at these moments, I usually, you know, feel very happy that I am not a mathematician, because I don't know why you need to prove something which I consider evident. But then, of course, my friends, mathematician, tells me that it's me an idiot and not them. Anyway, so assume that this is given. It's called monotonicity. That if you do projection, okay, now this is something which is, this is rho z, and this is mz, mx rho, okay? So you can see that this is S of z minus trace rho z log mz rho. It is this guy which would appear. So now let's look at this quantity. How I'm doing this time, I'm not very good, okay? So let me be real fast. So if I look at that mz rho x, it is mz mx rho. So let's do this projection. So first of all, I project rho on x. Okay? Gone. And then I project x on z. And that's my z state. Well, this is a matrix, right? So now I'm writing this matrix. Now I do the same procedure. I project x on z, and this is z state, okay? So essentially, what is written here is that there is a sum over z, right? And there is, let me squeeze it here, because there is no x to the left. And this is sum over x, okay? So now what I need to do, I need to take log of it. So I need to take log of it. I need to take log of it, okay? And when I take log of it, and those matrices are diagonal, okay, then essentially what I need to do, this is my elements of the matrix, I need to take log of this thing. So you put log over here, and then there is a sum over z. So you need to take log over here. Now what you say, that there are these projections. You see how they start to appear, these projections. So you say, okay, we do inequalities, right? We do inequalities. So let's just say that this is definitely less or equal, because it comes with a minus, I want it less or equal, than the maximum of x and z projection. So I will just replace this and this by its maximal value, okay? And so what would be here is a logarithm of maximum x z squared, because it's left, right. But the sum over x rho x is unity. It's just a normalization, okay? So after I took this and this out, this sum is just unity. So happily, what I get, if I now look at this inequality, and this is by definition s of x minus f of rho, so what I will get? I would get s of x plus s of z larger or equal than log, it comes with a minus, so 1 over max xz squared plus s of rho. That's the most general uncertainty relation that we have in quantum statistics. And it's nicely put together both sources of uncertainty. You see, it tells you have x and z. What you know about them, that they are non-commuting. There is some certain non-orthogonality between their states. But there is also the very fact that where you are working is a density matrix is not, okay? So the quantum statistics and quantum mechanics come additively in this form, and this is a restriction from below on entropy, okay? That's fundamental restriction from below. Questions? Good. So this is probably something which you would not be surprised, but just I want to put it nicely together. So now, what I promise you, we do restriction on uncertainty from above. And for this, we need to account for the existence of a very special regions of space which are called black holes. And black holes are, you would say, astrophysical object. Why we need to care about these astrophysical objects? And they follow from the fact that there exists a fundamental constant c, and there is a fundamental restriction that you cannot move faster than c. You may wonder how the hell it can any relation to information theory, the fact that you cannot move faster than c. Let's see how it has. It tells you that if you have a body with a mass m, right, and you want to escape from a radius r, then you have a potential energy, which is gm. This is your mass. This is this m mass, mm divided by r. To escape, you need your mv squared over 2 to be larger than this, right? So you need your v squared be larger than gm over r, but on the other hand, your v is less than the c squared. Okay? Now, it tells you that you escape when your r is larger than, let's call it RH, and RH is a horizon radius. It's 2gm divided by c squared. Okay, good. So you cannot, to escape, you need to be at least in this distance, right? If you closer, you cannot escape. So you have a horizon. A black hole is an object whose horizon is larger than its size, right? Because generally every object has its horizon, but normally this horizon is deep inside the object. So you can escape from the surface of the object. Now, all the story started again with a PhD student. The PhD student is Yakov Bekenstein, who was then, and he was a PhD student of John Wheeler at Princeton. Wheeler is a teacher of Feynman. Well, he did many great things. Also, a lot of him on YouTube. I very much, I'm just enjoying watching him on YouTube. So once Yakov told Wheeler that, you know, whatever you do with your system, entropy increase, etc., you just drop it into a black hole. No, Wheeler told to Bekenstein that you can drop it into a black hole and all this entropy disappears. So you can actually diminish entropy just dropping into a black hole. You know, no body, no uncertainty. As Comrade Stalin would say, you know, no person, no problem. No body, no uncertainty, okay? And Bekenstein was visibly, because it's in Wheeler's memoirs, he said Yakov was visibly disturbed by this statement. And he was a PhD student, I guess in his second year at the time. So he went out, and in a couple of months he came back and said, no, you can't do it because entropy, because black hole by itself has entropy. So if you drop something, you can only increase the entropy of the world. Again, it's something like a first law of thermodynamics. It's a religious statement, okay? It tells me, we believe that no matter what you do, the uncertainty in the world cannot decrease. Just a statement. Could be right, could be wrong. You say, assume it's right and proceed from here and see what are the consequences. So that's actually led to the entropy of a black hole. So what was the argument? And Bekenstein and Hawking and other people, and the idea was as following, that you need, you know what is the energy of a black hole, right? It's just mc squared. So to get entropy from energy, what you need? Temperature. Temperature is a exchange rate, bits per joules, right? That is how you get bits out of your joules. So you need to estimate a temperature. And so what is it? Namely, that you say that there must be some kind of a fundamental energetic things which is related to this something which has a size. And this is the size of black hole in a sense, right? So it has a mass, and this mass determines its size. So you can characterize it by mass, you can characterize it by size. And so it says it's the minimal temperature that you can think about just because there is quantum mechanics, right? Quantum mechanics tells you if anything is confined in a distance r, its momentum cannot be less than h bar divided by r. And if there is this momentum, then there is a related kinetic energy, which you can accompany by temperature. Or you can say that this is your temperature is h bar omega, and what is your omega? It's a frequency of a photon with this wavelength RH. Okay? Any way you do it, you say that there is a fundamental energetic thing, which is this one. Now, what is temperature? Temperature is, as we discussed many times, it's the derivative of energy with respect to entropy. Let's just write BH, black hole. Okay, but we now know what is energy. It is a mc squared. So let me express m in terms of, so it is c to the 4 divided by g, and it's a derivative dds of RH. So I expressed energy, which is mass. Mass is RH c squared divided by 2g, and there is another c squared, give me this. Okay, that's a differential equation on RH and S. And so you immediately derive from here that your S, black hole, is RH squared c cube divided by GH. It's a very interesting formula. First of all, it tells us that it's quadratic, not cubic. Okay? It's called area law. Namely, the entropy is proportional to the surface, not to the volume. Okay? Which essentially, if you think about entropy of anything of any size, at very large r, of course, well, let's say log. It's cubic, right? It has a slope 3. But at some point, when you're keeping the same mass, decrease your r. You squeeze more and more, it turns into a black hole. And then you don't see what is inside, so now it's quadratic. So this is r cubed, and this is r squared. Okay? RH squared. Okay? So this is a simple message, and so we saved our religion by assuming that the black hole is, but then Wittgenstein continued to thinking about it, and he came to what is now known as a Wittgenstein bound. And namely, he asked himself the following question. If you now have a body of the size r, right, and there is somewhere, and with an energy E, and there is somewhere a huge black hole with M, with its own RH, related by this formula, 2gm by c squared. And so now you take this and drop it here. You know how much the entropy of a black hole would increase. The entropy of a black hole would increase because it increases the mass. If you take this E divided by c squared, that's a delta m that you add to the mass, right? because RH is, let me write this in terms of mass, that RH is 2gm divided by c squared c cubed gh. So if you add here delta m, then this increases. An increase of the your entropy would be 2gm delta m. You know, I don't write any factors. So it will be m delta m, and divided by c squared, c to the 4, c cubed, gh. This is 2g, yeah, g squared. So now this is delta m is your E of your system, right? Divided by anything else. So what Bekenstein said, and this is a very elementary computation, I'll just show you a scheme, that if we take any body and we characterize it by its size and its energy, then we say that when we drop it into the black hole, the increase of the entropy of the black hole would be proportional to this energy. But this increase must be larger or equal, definitely not smaller, than the entropy of this system. Okay? And that imposes a restriction how much entropy a given system can have. Okay? So that's a simple idea. It again, and of course what I'm giving you is kind of hand waving, and there was now a lot of really very beautiful theoretical work which really tried to describe all the processes, how you actually move the body adiabatically slow, because you really need to reach this adiabatic limit. But let me give you the answer. And the answer is this following, that you can show that your S of any body is less or equal than r squared c cubed over gh, which is, you can write this, incidentally, as RH squared divided by LP squared. Your entropy is dimensionless. So what stands here is called squared Planck radius, which is the only combination of three elementary constants which has a dimensionality of centimeters. So non-surprisingly, you can write it as r squared over LP squared. Again, it's dimensionless, right? If it's r squared, again, you see the area law, and but yeah, it's also a kind of well, anyway, let's maybe keep it like this. So what you find out that the black hole realizes the limit when here is RH squared. So this is always less than this. When this is equal to this, when this is RH and your object is a black hole. But on the other hand, it gives you a fundamental limit. It takes you, take any physical system, exploit all its degrees of freedom down to all the lowest quantum degrees of freedom with all the spins and quarks and all this. It cannot be more information than this. You cannot squeeze more information. Because at some point when you start squeezing it, it would turn into a black hole and you see only horizon, and that's your entropy. So this is really surprising, and particularly surprising is G. You see how H, G, and C conspired to impose a restriction on a maximal uncertainty in a physical system. It's a huge number, but again, I mean, it's conceptually really very important.
So,
Yeah.
so what is the statement that entropy of any
entropy of anything which is inside size r could not be larger than this. That's it. Of course, you ask, what is this entropy? And it's quantum field theory, in the sense that there is vacuum which has this infinite fluctuation. So if you're really more accurate, the statement is as follows. Take a vacuum. Well, technically it has infinite entropy because it has all these zero fluctuations, right? Now, put at this place a body. Look at the difference between what you had before you put a body and after you put a body. This is actually entanglement entropy of your system with the environment. And if you ask yourself, where the hell this temperature appear? You want a physical picture to it? Again, different people have different intuition. My physical picture about this temperature is as following. So you have the black hole, and it has a horizon. But it's a quantum world. In a quantum world, out of vacuum always appears particles and antiparticles. Well, if they appear here, they appear and disappear, appear and disappear. But if it happen to be that the particle and antiparticle appeared and they straddle the horizon, namely the outside, this would never come out and this would come out. This is an evaporation of black hole, or its radiation, if you wish. So this is the temperature of this radiation. And of course, this is also the mechanism of entanglement, right? Because they are born out of the same. They entangled these pairs, right? So because they are entangled, when you register this photon somewhere here, it would know some information about a black hole, okay? And of course, there is a big discipline about all this evaporation and how it goes and why black holes eventually disappear. Questions?
So the entropy of usually of any normal matter would be extensive, right? It would be like volume.
Yes.
But this is so
In a sense, when we are at a very, very large scales, our density of matter is so low, then everything, it's like here. So if you keep your matter in a very large size, then it's cubic. If you, with the same matter, would squeeze and squeeze and squeeze, or another way you may say, if you are at some distance, at some radius, and try to put more and more matter. So what essentially it says, take R, okay? How much entropy? R cube, when it's very dilute. Okay, let's put more matter. So let's look at it from other perspective. Let's keep a region and put more and more matter into it, okay? So you increase entropy, right? So you put more and more matter, more and more spins, more and more everything. It increases, increases, increases until it turns into a black hole. Because now this size is less than the horizon. Up to this point, all your entropy is what lives outside, and this is this maximal entropy. Okay? So this is question. Speak louder, or we don't have mic.
So, if I'm not mistaken, the argument that entropy should be a convex function of energy was because it should be stable from breaking apart, right? So in this case, a black hole, to my knowledge, cannot break apart. So does the convexity?
No. Entropy is, it can break apart, but entropy of a black hole is RH square. RH is your mass. Mass is your energy. So it's kind of squared energy.
Is it convex? Energy is not additive.
Yeah,
right?
it's if you consider, well, it must be in equilibrium. I don't know to what extent you may consider black hole to be in
Thermodynamic object.
probably yes, yeah. Well, at least it's stable. It's a good question. I'll think about it. But it's stable. Black hole.
Is it in thermodynamic equilibrium though? I mean, that question might be how would it approach?
Good question. I don't know.
How would it approach?
You see, for
thermodynamic equilibrium?
us, the black hole is not a system, which means that we don't know what is inside. Which means that we cannot actually, what we call its energy is just its gravity, right? Is its gravity is just mc squared. But m is horizon, proportional. And entropy is squared horizon. So what we get that entropy is a squared energy, or energy is a square root of entropy. That's a relation, but it's not something about internal structure of a black hole and whether it's inside in thermal equilibrium, or there are kind of many planets and a lot of turbulence going on. We don't know and we cannot get it. The only thing we know is this is an entropy of a let me put it this way. This is the entropy of a radiation of a black hole. The only thing that we have accessible is this Hawking radiation.
Okay, so one more question. Is there a concept of an out of thermal equilibrium black hole?
Probably, I don't know. I'm not, I am information theorist, which means that I would only see, and my H bar, personal H bar, I mean, on my pair is equal to 0 identically, right? So when I write H bar, it's only when I'm interested on projection of it on information theory. Okay? So H bar tells me two things about information theory. In one case, it has this H bar in the numerator, and its uncertainty relation, and it bounds from below. In other case, it has H bar in the denominator, and it gives me from above. I find it interesting. Even more interesting, I find gravitational constant here. So in a sense, what we are exploring here, this may be the last thing that I want to tell you, is that black holes are gate out of this world, right? The fact that such gate exists already imposes restriction on how much information we can have. We never, at least as far as I know, explored a gate into this world, namely Big Bang, right? It probably also can tell us something fundamental. But the fact that gravity somehow is related to information, it's also in a very technical way. Most of the information we see around produced by what? By Jeans' gravitational instability of the early universe. Our universe had no structure because gravity started to break it into different pieces. Again, from this also might follow something fundamental about information theory. I don't know. Wheeler believed into it from bit. And there is also, I must mention it, some people try to derive gravity as a force from entropy. But it's long shot.
So
Yes?
the graph that you have plotted entropy versus R, it is first increasing it as RH square.
This graph that I showed here is if you keep mass. But you can plot another graph when you have your R fixed and you just add mass. And then you realize that kind of initially it's just R cubed, but when you put a lot of mass, that would be R squared. Okay?
So this is for R cube, means it is showing sudden increase.
At large distances, if you just keep the same amount of mass but make it less and less and less dense, at some point it will be R cube dependence. Okay? Okay, so what I promised you, maybe last few statements where I believe action could be in these directions, that a classical statistical physics, well, classical, I mean, non-quantum or whatever, of course, far from equilibrium states, in particular turbulence, which I'm working all my year. Somehow, these general principles that you're looking for the truth and nothing but the truth must hold. I spent 40 years trying to find out, even for simple systems, which condition I need to impose so that I would get this non-equilibrium distribution. We don't know. I think, well, there are simple classes in which we can do it. So in this direction, I think that really very important is to understand classes of universality of non-equilibrium system, and if any variational principle or extremum principle for which those non-equilibrium state, non-equilibrium probability distributions correspond. This side. And the biology is just unbelievable number of work because all the human genome we did not even start analyzing, which means that the hunger for people who know how to average logarithm is unbelievable. I mean, biologists, doctors, and all these people who just recently learned that there is Bayes formula. A son of mine who just got his bachelor in physics, but his wife is a biologist, did PhD in Columbia, and he taught her how to process the data because they don't know how to process the data, just usual data in the biological lab. And all the way to the brain, right? So the brain research, I think, is now undergoing revolution, just as we speak. Really undergoing revolution, putting there E minus TS, logarithm, all this simple machinery start working there. Random walks, all this stuff. Again, a lot of data, and we are good in not necessarily writing codes, but understanding algorithms of processing data, right? And of course, what I think is really not technical algorithms of stock trading or whatever, this was already good, and there. I came in Dublin, there was a meeting of stocks exchange experts in predicting rare black swans, they call rare events. And out of these people who worked at different stocks exchanges, etc., third get degree in physics. So this, I mean, they already exploited. But more fundamental questions about the nature of our economic activity, I think is something which is still not very known, and it can really tell us very important things about ourselves. And another thing which I think is very surprisingly start having moral projection, I would say, is our understanding how the brain works in terms of its plasticity. How much we can do about it. I think that we are, and again, it's all in the framework of this kind of information theory. For example, we used to treat emotions as something that we inherited from animals and then kind of developed living, right? So this is kind of some pattern of reaction. If our present developing theory of predictive mind and effective inference is true, or at least the right direction to develop, it means that also emotions are very, very plastic. We can taught ourselves emotions. I think that if this is true, this would have a huge moral implications for us. Technical, I mean, right? Because, so all this, and again, you go there, you speak to people on the language of free energy and entropy and information. That's a universal language in which everyone speaks to everyone, right? So that's why I think that it's good if you learn this language. Well, you know most of it already anyway. Okay? Good. More questions if you have on more irrelevant things.
I just have one question. So, so you wrote this equation like F equal to E minus Ts and then T equal to this money minus information.
Yeah.
I mean, so is this actually used in, for example, in economics and?
Yeah, in a sense, but in a very simple form, in a sense that you can want to estimate how you lose your purchasing power when you lost information, or in other things when they do kind of optimization. So they say that you really want to find a right balance. For example, all the strategies. There is a very beautiful. I have an appendix about it, but it's really a huge field. It's called index strategy, because when I talk to you about proportional gambling, Fi proportional to Pi. You need to know Pi. So you start going there and you need to learn it. You need to get information about Pi. But you also want to earn money. And it is this balance between what they call exploration and exploitation. That's what they usually do by designing a very
not so trivial two-term functionals, but a more non-trivial so-called index strategy and other. How actually you learn your PIs, but also trying to earn money in the process. So you try to balance these things. So in economics, this is, and again, almost anything that people use in economics, people use in biophysics. Because then you go and you understand that nature invented it before us and uses it. Okay? Question?
So is the index strategy similar to the horse gambling what the owners use, so that you look at the way people bet?
Index strategy is much, much more non-trivial. Index strategy is, in a sense, something like this. You need to choose. Imagine the situation that there are, it's called a multi-arm bandit. You know, if you go to casino, it is this. So you come to casino or you come to stock market. There are different stocks. You don't know which one is more probable to win. Okay? What do? You start playing once. First of all, you start assigning prior probability to all of them that they are equally probable to win, 1 over n. You take one, start playing, and you always, every win or lose, updates your probability of this guy. At some point, this probability is less than all the rest. Then you switch to another guy, okay? Which means that you, for every stock, you compute in, it's called Gittins index, and there are beautiful mathematics behind it, okay? And this is precisely, and now you start learning about next guy. Well, there are more complicated strategies where play, etc., and you update. But the point is that you balance exploration, learning probabilities, and exploitation, playing actually the game, betting your money. So it's really non-trivial.
I thought the index strategy was the John Bogle's ideas of market cap weighted.
Yeah, it's also, I mean, everything about game theory, but this is a very particular type of game. It's called allocation game. So it's, I'm not sure how directly it's related to Nash equilibrium, but it's of course from the same stuff, right? And of course, game theory is very much related to linguistics, but understood not as only information theory, but as theory of signals. Because signal is something which want to change the behavior of a receiver. It's not just information. And there is a beautiful signal theory, which is a part of a game theory, which is, of course, much more relevant to how our real language operates than just counting bits. It's much more non-trivial thing. And it's all related, and logarithm of a p log p is the center of all these disciplines. And convexity of it. And for Nash, too. Okay? Yes?
When you are using a pure state, then the uncertainty relations lower bound is basically log of max xz.
When you're in pure state, you quantum mechanics, you have usual Heisenberg.
When you are using the density matrix, the log max comes in the denominator, minus, is a minus.
Yeah, in a sense, when you're in a mixed state, you just add S of rho to your uncertainty. It increases your uncertainty. But when you are in what this max is just, you know, think about this 1 over d, right? It's just overlap between states. Okay? More questions? Good. So again, has any author, particularly I just finished, go read a book. What is good after you had this course, it will be easy for you to read a book because you're already familiar with language, style, etc. And it's a physics book. There are practically no proofs there, and I always prefer to give, you know, inductive example rather than very thorough definition, etc. But it, in a sense, it's panoramic. It shows you how wide is the field where you can apply P log P, and you already know it, so you can just do different things. Okay? It was a pleasure lecturing to you. Thanks for your attention.
So let's thank you for a fantastic set of lecture.